holding of the motion in space. So in physics, if a particle moves with position vector of t at time t, then the velocity vector is exactly the rate of change of the position. Okay, so v of t is the rate of change of r. Okay. So basically, we are trying to somehow start with the assumption that r of t represents the position of some particle, and then we can associate the physical meanings to the mathematical expressions. Okay. So the speed is the absolute value of the magnitude as a vector function. So the speed is just the magnitude of v of t. Right. And we also know that the acceleration is also a vector function, but the acceleration is the rate of change of the velocity. So acceleration vector is a of t equals to v prime, which is equals to just double prime. Okay. So the second derivative is important in this sense. Okay. So basically, the velocity is the rate of change of the position, and the acceleration is the rate of change of velocity. And then, if we do the antiderivative, that kind of process is also gonna hold true. Okay, so that's the fundamental theorem of calculus. So we have from fundamental theorem of calculus. So velocity is the integration of the acceleration so here recall basically if you are integrating some function, let's say h prime of t, right? So basically what do you know? So you are integrating h prime, you are assuming that the antiderivative of this inner function h is something that you know, right? So then you just evaluate h at t equal to a and t equal to b at the endpoints, right? So this is exactly h of b minus h of a, right? So that's exactly how you're getting this kind of equation. So then add both sides by h of a, you will get h of b, the end output is going to be the starting output plus the definite integral. Okay. So that's exactly how we are getting this accumulation of acceleration, right? And then the same thing happens with the accumulation of velocity. Okay, so r of t equals to r of 0 plus the integral from 0 to t of velocity. But now the variable that we're integrating is different. Okay, so here we're looking at the vector functions in terms of t. So the integrals here are in terms of u. Okay. So that's the only difference. remark. So given a of t, the acceleration, and the initial velocity, we have the velocity at any point. Okay, so the initial velocity is actually very important. Okay, and also when we are given the velocity at any point and the initial position, we have the position at any point, at any time point. Okay. Example. Let's look at the position vector with respect to time is RT equals to cosine of t I plus sine of tj. So in this situation, you'd be okay. We have x, y components, right? And they are trig functions. So you know that x squared plus y squared is 1. We are circulating around the unit circle. And then there's the z component is 0, right? So to illustrate, we are on the unit circle in the xy plane. So basically, when t is 0, we are at the point 1, 0. Right? And now, if you think about the location, let me think. Yeah. Okay. So let's quickly calculate the velocity and the accelerations. Okay. So we have v of t is the rate of change of the location. Okay. So we have what? So r of t is cosine of t, sine of t, right? So we just do component-wise derivatives. So cosine gives you a negative sign in front of I. And then sine gives you a cosine in front of j. So this vector function v, the velocity, if you think about it, it's also along just on the a unit circle. Basically, the magnitude is 1, right? And then if we do the derivative again, so that's going to give us the acceleration, which is v prime. And we just do component-wise derivative again right here. So sine gives you cosine. So negative sine gives you negative cosine. Cosine gives you negative sine. And you notice, the vector A here is exactly the negation of R, right? So for instance, if we want to just put everything down in the figure, so let's say, for example, let's pick a time. At let's say t equal to pi over 2. Okay. So when t equals to pi over 2, so our location r of pi over 2 is what? So basically, when t is pi over 2, we're at this location right here. So t equals to pi over 2. So cosine is a 0, sine is a 1. So the location is j. So if I put it in black, it's this black vector, right? So that's my r of pi over 2. Right? And then if you also do the evaluation, v, the velocity at pi over 2. So here sine is a 1, so it's a negative I. Cosine is a 0, so there's no j. Okay? And negative I is what? Negative I is against the direction of x, okay, with 1 unit. So that's actually this one. right here. Right? And you see, okay, so basically, if you think about it, we are traveling, so on this unit circle, we're traveling counterclockwise, right? So basically, at the point t equal to pi over 2, this is definitely going along the direction of the trajectory, okay, the way that you travel, counterclockwise. That's v at pi over 2. Okay. And finally, the acceleration, if you plug in pi over 2, so we see that's negative j. Okay, so negative j is exactly the negation of the location vector. Right, so excuse me. Exactly this one, right? Pointing towards the center of the circle. And yeah, so that's A. Okay. So here, observe that in circular motion, in this situation, we have the negative of the vector function equals to the acceleration. Right here. Here. Any questions so far? Yes,
Yeah, so for v sub positive pi over 2, is that negative I hat?
negative I hat, exactly. Okay, which is something you expect, but you are traveling counterclockwise, so at the point, so you're going along this direction, right? So at the point in solid red right here, you're expecting it to go to the left, right? So that's exactly a negative I. So along the direction of negative I. Right? Any other question? Okay. Now, here we have another example that's longer. Example. A projectile is fired with initial speed of 10 meters per second. Angle of elevation is pi over 6 from a position 10 meters above the ground. Suppose the ideal situation i.e. there's no external force and the gravity has magnitude of acceleration 10 meters per second squared. So basically, we are given the location of the particle, excuse me, the location of the projectile at the initial time. We give you the speed, we give you the direction along which it travels. But then we suppose that besides the gravity, there's no additional external force. Okay? And here we want to do the projection. We do want to do the prediction. Where does it hit the ground? At which speed? Right, so now quickly summarize what the information that we have. Okay, so basically, we can just try to utilize that the direction that we're traveling. So that's gonna be within the same plane, right? So we're gonna call that plane XY. So the X is the sort of the direction along which the projectile is flying towards. And the Y direction is the vertical direction is about the elevation. Okay, so it says it's 10 meters above the ground. So let's say 10 is right here. So this is the start point, right? And then we have the gravity, which is an acceleration pointing downwards, which is also 10. You see, the acceleration is exactly 10. So the acceleration is actually this one, okay? And what else? We have the speed is 10, it's a vector. And we know the angle of elevation is pi over 6. So basically, this is flying upward with an angle 30 degrees, right? So pi over 6. Okay. So basically, the initial velocity is the speed is 10. Okay, the direction is given. So we want to calculate the components in terms of x and y. Okay? And once we have the initial velocity, the initial location, we should be able to give a prediction. And it's going to be a parabola, and then it will hit the ground at some point. And we just want to know what this point is and what the velocity is. Okay? So before I let you guys go, quickly we break up the initial velocity. Okay? So basically, here, this direction is having an angle pi over 6 right here, right? So if you are looking at the unit vector along this direction, then basically, take a look. This hypotenuse has a length of 1. Right? So unit vector. So that tells you what? That tells you the opposite edge has a length of sine pi over 6, which is 1/2. Okay, and here this is cosine pi over 6, which is square root 3 over 2. Okay, so that gives you the xy components of the vector along this direction, right? So b0 here is exactly 10 times square root 3 over 2 I plus 1/2 j. Okay. Basically, the information that are important are on the left side of the figure. Basically, the location, you see that 10 is actually the initial, well, this solid dot in black, that's the original location R0, right? And then you are given the velocity v0 in a not so explicit way, but you are able to calculate the vector, right? And then what are you looking for? You're actually looking for the location at which it hits the ground. So that's actually we want to know what the time that is, right? And also we want to know the location R of t given at t, and also we want to know the velocity so that we can calculate the speed. Okay. And basically we summarize. So the initial position is R0, which is 10j. And then, we know that the magnitude of the velocity is 10, so it's gonna be 10 times the unit vector direction that we calculated. Okay, and once we're given that, it's pretty standard. Basically, we just apply that fundamental theorem of calculus. Okay, so we utilize the acceleration. You see, the acceleration is negative 10 in our problem assumption, negative 10 meter seconds meter per second squared. Okay. So basically, we just do the integrations. We realize that velocity at any point is going to be the initial velocity plus the integral of the acceleration. Okay. And then, given that, we're able to integrate the velocity from 0 to any time point t, and add up with the initial position to get the position at any time point, right? And of course, the velocity here is a linear function in terms of t, right? And then eventually, the position is a quadratic one. Okay.
Could you go back up for a minute, please?
Well, the notes is available online, so basically I'm just quickly going over it. So here, there isn't a lot to say, but basically at the end, you just want to calculate when the vertical position is 0. Okay, so basically we solve it, and then we get two solutions. One of them is -1, and the other one is 2. And then we'll be able to know that, okay, that t we want is actually 2 seconds after the starting point, and then we just evaluate. That R of 2 is 10 square root 3, I, just 10 times square root 3 units to the right, right? And then the velocity v2 is just what you just plugging it right here. Okay. Yeah, so basically, this kind of question, I would say it's not really complicated. It may appear, it may not appear in the actual exam. But I would like to mention also that there's a project 1 that's somehow related to this kind of question. So here we have a projectile that's just fired. But then possibly in the project 1, if you look at that PDF file, there's actually a YouTube link that's about when you're holding a dart and you want to throw it at the dartboard at the wall. You want the dartboard to travel on the wall so that whatever direction that you throw at your dart at, it will the dart will always hit the bullseye. So that's a kind of interesting program that you can write out to give this kind of prediction. So still, the idea here is kind of fundamental, right? So basically, yeah, you integrate the acceleration, you get the velocity. You integrate the velocity, you will get well. If you integrate the acceleration, you will get the change in velocity. You integrate the velocity, you will get the change in position. Right. So make sure to look at the details of this note that we shared.